what does that mean for a number to be divisible by another? So the number m is divisible by the number n if there exists a number p such that m over n equal p, which basically means that m is equal to np. Now, we are going to use this to demonstrate that an expression is divisible by another number, and we'll do that by induction. So again, let's do an example. Example 1, prove by induction that for all n greater or equal to 1, 4 power of n minus 1 is divisible by 3. Okay. Again, 3 steps. So step 1. For n equal 1, so 4 power of 1 minus 1 is equal to 4 minus 1, which is 3, divisible by 3 indeed. Okay, so step 2. Let's assume that the assumption is true for k, i.e. there exists p belonging to z such that 4 power of k minus 1 is equal to 3k. Now, for k plus 1, so 4 power of k plus 1 minus 1 is equal to, well, so we need to use our assumption. How can I fit that into this expression? Well, I can rewrite 4 power of k plus 1 as 4 times 4 power of k minus 1. And then this, using our assumption, is 4, okay, because our assumption is the same than 4k is equal to 3k minus 1. Oh, sorry, plus 1. So therefore, I can rewrite as 4 times 3k plus 1 minus 1. And so that's equal to what? 12k's plus 4 minus 1, which is 12k plus 3, which can be written as 3 times 4k plus 1, and 4k plus 1 is an integer. Therefore, 4 power of k plus 1 minus 1 must be divisible by 3, as there is a 3 at the front. Okay, so now step 3, which is the conclusion. So it's true, the assumption is true for n equal 1. Then the assumption is true for k plus 1 if it's true for k. Therefore, by induction, it's true for all n greater or equal to 1. Good. Let's do another one. Example 2. Prove by induction that for all n greater or equal to 1, 3 power of n plus 7 power of n is divisible by 10. Actually, for all n and n odd. Important. N odd. Right. So step 1. For n equal 1, so 3 power of 1 plus 7 power of 1 is equal to 10, which is divisible by 10 indeed. Now, step 2, we assume it's true for k, where k is an odd integer. So that means that 3 power of k plus 7 power of k is equal to 10p, where p is an integer. Okay, so in that case, now the next odd integer is k plus 2. So for k plus 2, so 3 power of k plus 2 plus 7 power of k plus 2 equal, okay. So from this one, what we can do is we can rewrite 3 power of k. To use our assumption, we just need to reorganize the equation here. So it's 10p minus 7 power of k. So therefore it's equal to, you know what, let's move that somewhere else. 3 power of k plus 2 plus 7 power of k plus 2 is equal to 3 power of 2 times 3 power of k plus 7 power of k plus 2. Now, we use our assumption to replace this, so it becomes 9, because 3 power of 2 is equal to 9, times, and then 10p minus 7 power of k plus 7 of power of k plus 2. So, right. Let's expand that a bit. So it's 90p minus 9 times 7k plus 7 power of k plus 2. So, okay, so that's 90p. And then we can factorize by 7 power of k. So that's plus 7 power of k times 7 power of 2 minus 9, which is equal to 90p plus 7 power of k times 7 power of 2, that's 49, minus 9 times 40. So, okay, we can factorize by 10, so it's 10 times 9p plus 4 times 7 power of k. Now, this is an integer, and because there is a 10 at the front, that means it's divisible by 10. So, therefore, it's true for k plus 2 if it's true for k. And then step 3, okay, I'm going to be a bit faster. So it's true for n equal 1, and then it's true for k plus 2 if true for k. Therefore, by induction, it's true for all n greater than 1 odd integer. That's it.